Skeletal muscles cells are stimulated by a nerve impulse. The end of a nerve connecting to a muscle is called a motor end plate. Okay, there's another term, motor end plate. So that's the nerve connection to the muscle. That's right here. That's weird looking spready thing. The neuromuscular junction is an area where the nerve and muscles connect. So that's these. We saw that actually right on this slide over here. Oops, sorry about this. Right here, this is the neuromuscular junction right here. One nerve can stimulate a varied amount of muscle cells. So and then when each time in that one nerve, here it's a few cells, you see there's one nerve does a few cells here, and another nerve does a few cells here. But each time that nerve contracts, that nerve fires, all the fibers that it innervates will contract. And the motor unit is that one nerve and all the muscle fibers that it innervates. So we call that a motor unit. And that's an important term because each motor unit consists of a few. It can consist of a few fibers, or it consists of many fibers. If it only consists of a few fibers, its contraction is greatly in fine motor control, but it's weak. If that one nerve innervates many fibers, we have a crude contraction, but it's much stronger. And so we can grade what a muscle needs to be doing. Is a muscle a quad that needs to straighten a leg out or hold up a body and kick a soccer ball? Or is it a facial muscle that just needs to make a face, needs to make an expression? And so that's the motor unit is sort of that determining unit. And the more motor units that recruited at the same time, the stronger that muscle contraction is. So we can then grade each muscle contractions that way. We're looking at the muscle metabolism. We'll go right here. The only source of energy is ATP, and that's formed mostly in the mitochondria. So muscle needs a large amount of energy, so therefore it has many mitochondria. The easiest fuel source is when we take ATP from glucose. And so the muscle has a large storage space of glycogen, which is stored glucose, the glucose chains. They're stored in the liver and in the muscle, a little bit in part of the brain, but the muscle is a big one, so we always have that glucose available. So oxygen helps make rapid and numerous ATPs. Intense muscle strain, though, causes a lack of oxygen. So look at this here, this first thing here. This is oxygen, it's aerobic respiration, that's a mitochondria. We can mostly have glucose coming in, but we can also have fatty acids and amino acids come in. So we can convert those things into energy as well. This gives us a lot of ATP per glucose, and it gives us energy per hours. For hours we can do energy with that. That's really, really good. But intense muscle strain causes a lack of oxygen. And so what happens then, without sufficient oxygen, the muscle has to make the ATP anaerobically. So we move to this one over here. We don't have oxygen. So the glucose comes in and glycolysis breaks it down and gives us 2 ATP, which is not really great. And it also gives, it's not, compared to 36, there's nothing. And it also gives us lactic acid. Well, buildup of lactic acid has to be converted back to glucose by the liver. And lactate tires muscle easily. So that gives us energy 30 to 60 seconds. So you can do some fast, important, tough energy fast, but not more than 60 seconds. And then stored creatine phosphate is useful because we can take an ADP, which has, the ATP, the phosphate is pulled off. So now we can take an ADP and the creatine phosphate, take the phosphate, put it on the DP, and make an ATP and make creatine with it. But then we have to rephosphorylate that creatine after that. That gives us energy for about 15 seconds. Okay, that's not that bad. But that's sort of where we get the energy from muscle from, if you look at the whole picture. And so we have different muscle fibers do different things. A muscle twitch is the length of one muscle contraction. Some muscle cells are slower to contract. They're not as forceful step, but they can hold a contraction much longer. They sort of do this postural thing. Those muscles, they need to contract for hours, so they need oxygen. They harbor a large amount of myoglobin. And myoglobin is very similar to hemoglobin, and it can store a large amount of oxygen. But what's interesting, myoglobin is so strong to attract the oxygen. When the blood goes by the muscle, it just sucks the oxygen out into the myoglobin, and so from the hemoglobin. And so that's really kind of a cool way for muscle to get oxygen fast and get a lot of oxygen. Myoglobin colors the muscle red. So these tonic muscles, these postural muscles, are redder in the way they look. And then we have other muscles. They're fast and forceful, but they tire easily. They look more pale in comparison and are called fast and are also phasic muscles. And then we got these intermediate muscles, and they come in a whole bunch of variety. And that brings us to the terms of isometric versus isotonic muscle contraction. We have actually another term I want to bring in, but we have two different ways of contracting a muscle. We can contract a muscle that it changes its length. You can pull something up, for example. Here, we can pull that up. And when we do that, when we pull something up and something can shorten, we gonna use an isotonic contraction. The muscle length changes. The tone of the muscle stays the same, but the muscle length changes. We can pull the weight up. When we pull the weight up, that actually is known as an isotonic concentric contraction. When we let the weight back down again, the muscle also changes, so it's still an isotonic contraction, but then it's known as an eccentric contraction. Not a concentric, an eccentric. And then the other one is when a muscle fiber tenses up, but nothing moves. Everything changes, stays the same. That's known as an isometric muscle contraction. The term iso means the same. Metric in this instance refers to meter, which is a length measurement, and the meter of the muscle, the length measurement, stays the same. So that's how I remember that one. So we have isometric and isotonic. And when we discuss muscles, most skeletal muscles attach to bones, two different bones. Usually it crosses one joint. Some muscles cross two joints, but most of the muscles cross one joint. We have the attachments of the muscles to the bones. We need to describe those. So one attachment site is called the origin. And mostly this is the bony attachment that remains stable during a contraction. So it's the anchoring place. In the extremity, most of the time, that's the proximal attachment. That's the one closer to the trunk, closer to the attachment of the limb to the trunk. And then the insertion is the other one. That's the movable or mobile attachment. In the extremity, this is usually further away from the midline of the body, from the attachment of the limb to the body, usually more distal. A muscle that work together in unison to make a motion, for example, when we bring the arm upward, we flex the elbow, we're going to have the biceps, the brachialis, we even have the coracobrachialis help and stabilize. We have multiple muscles that work together, and those are called as synergists. The muscle that does the main movement is the agonist, or the prime mover, but then the ones that do the opposite, in this instance, the triceps is going to do the opposite than the front musculature to lengthen the arm back out. And that's known as an antagonist. And means the opposite. Something does the opposite. At the point of muscle attachment, a tendon anchors the muscle into the bone. The head is the beginning point of a muscle transitioning into a belly towards the center. And we can classify muscles by the way that muscle fibers insert into a tendon. For example, we have a parallel arranged fiber in a muscle that are long, go from the whole, where is the parallel? Go from all the way to the other side, from one side to the other side. Those are not that strong of fibers. Fibers that then though insert into a tendon at an angle, for example here, a unipennate, where the muscle fiber is angular and the tendon is long going up the muscle. But these are little shorter fibers that go into they can exert more lifting strength. So these are known as pennate muscle. Pennate means feather. We have unipennate, fiber inserting into a tendon from one side. We have bipennate, fiber inserting into a tendon from both sides. Tendons are bundles of collagen fibers with great tensile strength, and they transfer the force from the muscle to the bone. Remember, ligaments were bone-to-bone connections. Similar stuff. And flat tendons, like we had the one on top of the scalp, that's known as an aponeurosis. Aponeurosis. We have a few of them we're going to talk. And that brings us to the end. We have auxiliary structures. These are helper structures. Well, actually, that's a good question. Are they really helper structures or not? Or are those also main structures? In a traditional sense of the view, they are auxiliary structures. Some of them are becoming more important as studies go forward when we deal with treatment of musculoskeletal problems. The main function of these structures, though, is to reduce friction during muscular work so that there's minimal reduction of force. We have fascia, and those are gliding helpers. There are also wrapping pieces for muscle, and those are the things that become much more important because they have many more muscle nerve fibers that stimulate the brain and bring information back into the brain and decide what to do in terms of the output and muscle movement. But anyway, that we can talk much more about. Then we have synovial tendon sheath, and these are helping gliding of tendons over bony protrusions. Their structure is similar to joint capsules. They're filled with synovial fluid. And the bursa are different. Those are just like pillows. So the sheath are like here, for example. We have a sheath going around the biceps here. And the bursa lays on top. It's like a pillow that kind of lays in between structures that could rub a little bit too much. And then we got the sesamoid bones, and those are bones that are embedded in tendons, and they help with making the muscle movements more smooth and more continuous. And we talked about that already before when we talked about bones. Okay, great. Well, I hope you didn't completely die here, because physiology is not an easy one. It's a tough one. And so I think you probably did really well by sticking it out and hanging with me. Thank you.